In this video, we're going to learn a little about images and imaging. MATLAB has a very powerful image processing tools. Most of them are in this image processing toolbox. So there are a lot of toolboxes in MATLAB, and so one of them is for image processing. We're not going to use that toolbox. We're just going to do some low-level stuff. One thing what we're going to do is we're going to make an image. We're actually going to make an image. Just kind of old-fashioned way, just some arbitrary images and stuff like that. And then we're going to try to do this thing called edge detection. So why would you want to do that? Edge detection is in biomedical engineering is really important when you're trying to find like where the lung is and where the lung isn't in a chest x-ray, for example, that kind of thing. It really is an important tool to do to detect edges and stuff. And the way to detect edges, the edge of a filter is going to exist at where the derivative is the highest, when it goes from low light to high light, right? From darker to lighter shades. That's going to be the slope of that line is going to be the highest there. So we want to do the slope. We want to measure the derivative of a filter. That's what we're going to do. So we're going to manufacture some images that illustrate this point well, and then we're going to take derivatives of those filters, differences in this filter. So that's what this whole video is about. Okay? All right. We're going to start with making a new folder. I'm going to call that folder Sigmo for sigmoid, right? I want to make a sigmoidal signal because the derivative is the highest. I could have used a trigonometric signal or even some other type of signal, but sigmoids have a really, really steep from going from low numbers to high numbers. So I wanted to exploit that for the biggest effect. Good? Okay. Okay, so I make this folder. I go into Octave. I get into the right folder in Octave. And then I'm going to make a script, sigmo1.m. I edit sigmo1.m, and I'm not going to make an image yet. I'm just going to make a straight line. It's just a graph of a sigmoid is what I'm going to do. Okay, so x is going to go from -6 to 6, and we're going to put a pretty low increment on it. So there's several points, so it's nice and smooth, 100 and something points. And then and y is just the equation for the sigmoid curve. And then I'm going to plot it. I save it. I go back into Octave, and it gives me an error. It says near line 1, column 1. Well, the line 1 and column 1 are fine on my script. What's going on? This has been happening to me for a little bit. And so there's two things you can do. I'm going to go rename it. I'm going to go name a different one, and it's worked fine. So I'm going to do that. The other thing you can do, which I think also works, this is a quirk for Octave, not MATLAB. So if you're using MATLAB, ignore this little snippet of this video, is if you close up Octave and then just double click on the M file from the file manager system, right, from the file folder, you can, it comes up right, and then it works. So I don't know what's going on. Anyway, you can either rename it to be something else, or you can just exit Octave and come back in through a different way. Okay? All right, so I called it DrO Sigmo1 is what I called it. Then when I renamed it and I reopened up Octave and all that stuff, and I ran DrO Sigmo1, it came up, and you can see the sigmoid curve. That's the sigmoid curve. It's really, really steep right there at x equals 0. Good. That's a sigmoid. I'm getting to imaging. Don't worry. We're going to make an image. We're going to make an image out of this kind of. I want a signal that will go up and down and up and down and up and down, right? So I want to make a sigmoid and then a backward sigmoid and then a sigmoid and the backward sigmoid and back. I want a signal that is this and then the reverse image of this and then this and the reverse of this and this and this. I want to make a row of an image that way. All right, so that's the next step. All right, well, there's a function called flip. There are flip functions in MATLAB and Octave. Flip left, right, flip up, down. So I want flip left, right. I want to flip this row so that it's the last one is the last element of the new vector is the first element of the last vector, and so on. So I do that. I say a YF equals flip LR of Y. And then I'm going to plot both of them, and you can see that it flipped. It successfully flipped. That's good. Then what I'm going to do is I'm going to make a row. I'm going to call it row 1. And I'm going to use square brackets, and I'm just going to concatenate all the y and yf, then y and yf, then y and yf, separated by spaces. So it's all one big long row. And it's and the length is 6 times the length of y. Okay? When I plot out row 1, I don't have an x-axis for that. I'm just looking at row 1 now, right? You can see that it goes up and down and up and down and up and down. It's just sigmoids back to back, right? So this is this thing that I'm going to make an image out of. I'm going to make an image out of this. So far, so good? Everything look good? Yeah. All right. Before I get to an image, though, I want to take the derivative of that signal. I want to see what the derivative of the signal looks like. So the derivative is just d rho's dx, right? So the if the x-axis, you're just taking the derivative of this variable rows with respect to the x-axis. It's not d, right? Because this is not a continuous variable. This is a discrete array. This is just a list of numbers. So then you don't take the derivative, you take the difference. So it really would be rho of 2 minus 1 divided by delta x, right? I don't need the delta x per se. I just am looking at the difference between 2 minus 1. So I'm going to take the second number minus the first number for the whole row. You can do that all in one line. You can vectorize that, and that's shown here in this figure. Filter row 1, 2 to the n. The second through the nth amount of filter row 1 is equal to row 1, 2 to the n, minus row 1, 1 to the n minus 1, right? So you can do it all in one vector command. N is the length of row 1. So I calculated that out. Wow. Okay, let's look at it. I want to look at that. And so you can see both the unfiltered row and then the filtered row. It's the derivative of the bottom figure, the bottom graph, one two-dimensional graph, is a figure of is a derivative of the signal in figure 1. It's really, really high when the slope's going up. It's really, really low when the slope's going down, and it's pretty much 0 everywhere else. It's a nice little spiky signal. That's why I picked the sigmoid. It really illustrates the derivative pretty well. Cool, right? Okay, so that's the basics. That's the basics of how to take the difference, how to take the derivative of a signal in MATLAB, a numerical signal, a numerical vector in MATLAB. So far, so good. Now I'm going to make an image. Okay, so you could do this a vectorized way, but I didn't. I just did it with a loop. So I want to make a square image. So I want it to be as many rows as it is columns. And so I made a for loop, for I equals 1 to n, and say the unfiltered image, the ith row of the unfiltered image is just equal to row 1, right? It's going to be the same. Each row is going to be exactly the same, so it's going to be stripes. And when I show the image, instead of plot, the way to look at an image is just a x and y. There's no x-axis, y-axis. You can do 3-dimensional plots, by the way, in MATLAB and Octave. That's cool too, but I just want to look at this matrix, right? It's no longer a vector. It's no longer 1 by n. It's going to be n by n. So now it's a matrix, and that's all an image is. An image is just a matrix of numbers. And all these numbers are between 0 and 1. And so the brightness of the signal, the brightness of this image is going to be whitest when it's 1 and darkest when it's 0. That's it. All right. So the way to do that is with the command imshow, show the image. Good. I have the return down there because I left some little code at the bottom, and I didn't want it to run that code, and so I just put return. That's a way, if you have some junk at the bottom of your script, just to stop the script. Just say return. Don't do any more on that script. It's kind of a way to put a break in the script. Okay. So now when you see when IamShow comes up and you see the image, you can see that it's just a 3-dimensional version of that 2-dimensional graph that I had there, right? Right? It's just rows of these stripes, bright stripes and dark stripes, bright stripes and dark stripes, all down the road. Cool. All right, so that's the image. I want to take a derivative filter of the image. Image filtering. There's all sorts of ways to filter images. And this is going to be a little 1-minute side item here, is that I know that I've taken classes in image processing. I know there are image processing techniques. There's things, and so if you're an image processing person and you're watching this teaching students and you're having angst or something like that, relax. I'm not going to talk about the following terms: convolution, kernels, all that stuff. I know that it exists. This is just to get you started on learning MATLAB and Octave and the potential power of those tools. And by the end of this lecture, by the end of this lesson, they'll know, wow, I need to learn a lot more to actually do this right. We're not doing this right now. We're just doing kind of like a little kludgy beginning lesson in Octave and MATLAB. So when one gets more sophisticated in how to really process images and filter images, then there's a whole class on it. You got to take a class about it. But this is a good first step. This is kind of an interesting whetting your appetite for image analysis and image processing. Filtering is a way you can filter an image. You can take the average of little sections, right? If I took the average instead, it would blur it out. It would smooth out lines. If I take the derivative, it sharpens edges. So that's kind of what image filtering does. And then, by the way, there's a lot of other ones. There's Gaussian and Sobel, and there's all sorts of image filters. So I'm way oversimplifying this very, very complicated, sophisticated issue. If you really, really get interested, you got to take a course in image processing. Okay. Good so far? Yeah. All right. So now I want to filter this image. I want to do a derivative filter, an edge detector. So I go in and I do the exact same command that I did for just the lines, right? When I took the derivative of it. Comes up. It's just dark. Doesn't do anything. Oh, let's go back to the straight lines and look at it. So the upper thing, it goes from 0 to 1. What's the y-axis on the filtered signal? It goes from 0.02 to minus 0.02. It's tiny. First off, it's centered around 0. That's not good. We want it to go between 0 and 1. Second off, the whole range is 0.04. That's really, really tiny. We need to make the average value 0.5, right? So if there's no derivatives, it's kind of grayish. And then we need to scale it up so that it's kind of in the same scale as the first image. You can't see anything. It's just too dim because the rate of the change in the color, the change in the scale is just so low. All right. Okay. So in order to do that, I just changed. I made a vector that's called half. That's just equal to 0.5, and it's the same length as each row of the unfiltered and the filtered image. And then I say it's going to be half plus 20 times the difference, right? So 20, that'll get it up to 0.1 and 0. That'll make it the range the same. So I just amped up the difference and added 0.5 to every number. And so every pixel in this case, if it's an image, and that ought to work. Good? All right, so now when I run that script, you can see that when the upper image is going from dark band to light band, you see a big white stripe. When it's going from a white band to a dark band, you see a big black stripe. And it's gray in the middle, right? So it's gray everywhere else. So it's that white is detecting that leading edge, the edge that's going from dark to light. And then the black line is detecting the trailing edge, the edge that's going from light back to dark, as you go from left to right across the image. Cool. Oh my gosh, that's cool. Right. Okay. So now I can detect where those edges of this upper image are. That's pretty cool. I have a new image that's the edges of the first image per se. It's not great because it goes up and down. So I'm going to fix that. Let's fix that. The way to fix that is just to use the absolute value. So I just want to see the absolute value. Everywhere there's a change, either from light to dark or dark to light, I just want a bright stripe. I don't have to add half anymore. I can just make it be at 0 and just use ABS. I can also multiply it by more. So I'm multiplying it by 40 instead so that it's a bigger signal by the end. Good? Let's do it. So I run that, and now we just have these stripes, right? Jack White would be proud. I've made the white stripes on the bottom image. Okay, so now I've got an edge detection algorithm. The derivative filter is an edge detection algorithm. Cool. I am starting to get interested in imaging now. This is kind of exciting, and again, we're just doing really rookie stuff here. So you know, this is not the official way to do this. There's a lot better ways to do this, right? But I just wanted to get you guys started in thinking about how you can manipulate images with math. Okay, so far so good. All right, just want to add now what I want to do is I want to make a two-dimensional image. So I made a new, I'm making a new script. I'm going to call it DrO Sigmo 2, right? For a two-dimensional sigmoid. I'm going to make a kind of a saddle looking thing. So it's a two-dimensional sigmoid. So I go in, I say edit DrO Sigmo 2.m at the command prompt. Right about, by the way, above there you see me calling DrO Sigmo 1 a bunch of times. That's all I did. When I was running it, I just called DrO Sigmo 1 at the command window in Octave or MATLAB. Okay, so now I made this DrO Sigmo 2 function, and I made an x variable and a y variable, and then I made a nested loop that goes to n1. N1 is the length of x; it's also the length of y, and I have a nested loop that goes 1 to n1 in both the x direction, the I direction, and the y direction, j direction, right? And so I make a variable xy. Xy is equal to x sub I times y sub j. Then I do the sigmoid calculation. So z is going to be the sigmoid of these x and y range here. So I'm going to fill it out. In MATLAB and Octave, there are actually ways to generate this kind of stuff. You don't have to do it manually with a two-dimensional loop. I just did it that way so that you could see what I'm doing, right? So you can actually understand, wow, that's how you fill out this graph here. And you can see the image when I run it. When I type DrO Sigmo 2 at the command prompt, you can see this new image. It's lowest at the top left, top right, and bottom left corners, and it's highest at the top right, top left, and bottom right corners. Cool, it's a saddle. It's a kind of a sigmoidy thing. Good. All right, so now what I want to do is I want to make an image out of that. So I'm going to do a row of this whole matrix, right? So I do the same thing. I flip it left to right. I have ZF equals flip LRZ. And then I make row 1, right? Which is just going to be Z, ZF, Z, ZF, Z, ZF. You can do it. I did it with just a 1 by n vectors. You can do this with matrices too. You can add up matrices this way. When I print out that row 1, you can see now I've got this kind of the beginnings of a checkerboard pattern, this blurred out checkerboard sigmoidal pattern. How do I make the full image? I want to make a square image out of this. Oh, I'm going to flip it up down. I'm going to take row 1, I'm going to flip it up down, and then do the same thing. I'm going to concatenate those in the vertical direction. Aha, let's do that. The way I'll do that is I'm going to say row 1 F, so flipped. The flipped row 1 is going to be flip up down, flip UD of row 1, right? And then I'm going to concatenate the image. The unfiltered image is going to be row 1 semicolon row 1 F semicolon row 1 semicolon row 1 F semicolon. So when you're trying to stack things up vertically, you separate them with semicolons. When you're trying to stack them up horizontally, you separate them with spaces. Just like the very first videos when we were making a matrix, exactly the same, right? It all works the same way. Cool. So now when I look at unfiltered image here, it is this weird sigmoidal checkerboard pattern. It's fuzzy, right? It's not like a real checkerboard pattern where it's a black square and a white square and there's nothing in between. I made it intentionally. I made it sigmoidal so that there's fuzz in between. So I'm going to do the exact same filtering that I did before. The only difference here is I'm going to lower the amplitude a little bit. There's a reason for that. I don't want it to get too saturated. So I made it 10 instead of 40 for the difference between the two. And then I'm going to go left to right. So I'm filtering left to right, and you can see at the output you get this kind of strange pattern where it's brightest between in the left to the right sense from the light circle to the dark circle, to the light circle to the dark circle. You see kind of a square, a peak there between the two. Well, what if I filter it a different way? What if I filter it top to bottom? Let's try that. So I go back and I just change the code so that I'm going to filter top to bottom instead of left to right. And you can see that the pattern is different. Instead now you get the little bright squares from between the light the light circle to the dark circle to the light circle to the dark circle vertically, not horizontally. All right, I'm going to take that. Let's do both. I'm going to do both. I'm going to do I'm going to do left to right filtering, top to bottom filtering, and I'm going to take the average of the two. Right? So then I do that. So you can see the code there for taking the average of the two. When I do that, wow, I get perfect edges around each of these kind of circles that have shown up here. The light circle, the dark circle, and then it's kind of gray in the middle. Wow, that's kind of edge detection. I sort of did it. It's, by the way, I know this is, if you're an image processing person, I know this is wrong. I know I know there's all sorts of stuff to do, but this is just kind of to sort of show you that you can do numerical manipulations. You got to learn the right mathematical rules and all that stuff. So there's all sorts of other stuff to go on, but this is just step one. This is step one to opening a door to some really, really powerful ways to mathematically manipulate images.